So the method of joints helps us solve for the forces in the members of a truss. And the theory behind it is that because the truss is in equilibrium, all of its joints are also in equilibrium, or in other words, they're not moving. So in order to analyze a truss or design it, we need to understand the forces that are going on in each of those members and to know whether they're in tension or compression. And so in this video, I'll be going over the steps on how to solve for those forces in those members. And if you find it helpful, please subscribe. So our first step is we need to draw a free body diagram of the situation and label all the known and unknown forces. We need to replace all the supports with support reactions, and we need to set up a coordinate system. Next, we need to see if there are any zero force members to help try to simplify this. If you don't know how to do that, you can check out this video. And then we need to solve for those support reactions. And we can usually do that by summing moments about one of those points where the support was and solve for the other support forces. And after we found the support reactions, we will then go joint by joint and set up our equilibrium equations to solve for the forces in each of those members. And to explain this better, I have here an example problem where we go over how to solve for the forces in each of these members. So what we have here is we have a truss that it's supported by two pin connections that are 3 foot apart, and the truss is 4 foot high. We have two loads up here at the top, and we're going to solve for those forces in each of those members and say whether they're in tension or compression. So what we need to first do is we are going to set up our free body diagram, and we're going to draw our coordinate system out here just to keep our free body diagram a little bit cleaner. And we are going to have our members drawn out like this, and our force of 600 pounds, and we are going to replace this 800 pound force with its components. So our X and Y components of that, so that when we set up our equilibrium equations, we already have those forces broken up. And so if we want the X component of that force, it will be 800 cosine of 60 degrees equals our X component. So the cosine of 60 degrees is 1/2, so 1/2 times by 800 is 400 pounds, and so that will be 400 pounds is our X component of that force. Now 800 times by the sine of 60 degrees is the Y component of that, and that will end up being rounded off a little bit. It'll be 693 pounds, and so it'll be 693. And so make sure you're setting up this right. I go over all my example problems before I record the videos, and when I was doing it, I swapped those two, and throughout the whole rest of the problem, I had those reversed, and so I ended up getting the wrong answer. And so I did everything right, I just had put in the wrong numbers because I had them switched. And so make sure you keep track of things like that. And so now we're going to label our reaction forces. This will be, we'll call it F sub A sub Y, and then we have F sub A sub X. And again, at point D, we'll have F sub D sub Y and F sub D sub X. And the reason why there's those two forces there is because it's a pin connection. If it was just like, say, a roller connection, it would only have your Y component of these forces. If it was a fixed connection, you'd also have a moment reaction. But with it being a pin connection, there's only those two forces. So now we have all of our forces labeled on our free body diagram. And we're going to look now for zero force members. And looking at this, by observance, we will notice that there isn't any. And so moving on to solve for our reaction forces, we can observe that here, if we sum forces about point A, if we say the sum of the forces in the x direction equals 0 because it's in equilibrium, well, the only force acting here in the x direction at point A is this reaction force. So it's going to be F sub A sub x. But since there's no other forces there, we can tell that it equals 0 because it is in equilibrium, so there has to be no force there. And so we'll just erase this, showing that there is not an x force there. So now what we want to do is we're going to want to sum moments, and you could sum moments about any point, but if we sum moments about point A or point D, that will help us eliminate one of these, or maybe even several of them, so that we can solve for a remaining reaction force. And so it doesn't really matter which one you pick. I'm going to sum moment about the point D, and that way both of these reaction forces and this component of the 800 pounds, they're all passing through point D, where their lines of actions are. So there is no rotation created by those. But if we sum moments about point D, it's in equilibrium, so it equals 0. And so you're going to have that your 400 pound force is causing counterclockwise rotation. So we'll say that that's positive. That's 400, and this is 4 foot tall, so that's going to be 4 feet away, so times by 4. Then plus, because this force, 600 pounds, is causing counterclockwise rotation about point D, so it'll be 600 times by, its line of action is 3 foot away from point D, so times by 3. Then our force Fa sub y is going to cause clockwise rotation, so it's negative, and it is 3 foot away, so multiply it by 3. And you're going to solve that out, add this over to the other side, multiply these together, and then add them together, and you end up, and then you'll divide the 3 over, you'll end up at F a y equals 1,133 pounds. And because it came out positive, we know that we drew our arrow in the right direction. If it came out negative, it would be that our arrow is going in the wrong direction. And so that's kind of how we can tell whether or not we've drawn our free body diagram in the right direction. And so we're going to relabel this 1,133 pounds. Okay, to solve for the other reaction forces, you could again sum moments, say about point A, and then you could solve for force Fd sub y, or you could just do the sum of the forces in the y direction, which is what we're going to do right now. And so this is the forces on the whole truss, and our y forces is this reaction force 1,133, got the minus 600, and you have this minus 693, and then your last one is F dy. Okay, so you'll add all that up, subtract that over, and you'll end up getting that F dy equals 160 pounds. So we'll relabel that here, 160. That is in pounds. Okay, so the way equilibrium equations work is that in order for there to be equilibrium, the structure has to be not moving. And so the forces will cancel out, and because there are only 2 external forces on this truss that are going in the x direction, we know that for there to be equilibrium, they will have to be equal magnitude. So we will know that Fd sub x is going to also be 400 pounds because there's only those two forces acting in the x direction on this truss. So 400 pounds. Okay, so now that we solved for our reaction forces, we can now pick a joint that we want to start off with, and remember that it has to have at least one known force and two unknown forces. No more than two unknown forces. It could have less than that. But if there's more than two unknown forces, then we don't have enough equilibrium equations to solve for those. And so we can see here, say at point B, that we have one known force, but each of the forces in these members is going to be an unknown force, and there are three members coming off of point B, so there would be three unknown forces there. So we're not going to want to start with that one. Again, at point D, there are two members, but this member BD has an x and y component of the force, so it also has three unknowns. And this one had four unknowns, so we don't want to pick either of those. So looking at point C and point A, this one's going to have two unknowns, it has two knowns. This one has one unknown and one known. So we can pick either of those to start off with, and it doesn't really matter. In this case, I'm going to start off with point C. So just to remind us that we're at point C, I'm going to say at point C, we're going to draw a free body diagram of that joint. And so that looks like this. We have our member CD coming here. So we'll say CD, and we have our other member here, which is our member BC. And we have our external forces acting on that, this one being 400 pounds and this one being 693 pounds. Well, we're going to label our internal forces of these members FDC or FCD and FBC. And just by observation, the way we're going to draw these is going to be opposite of these forces so that there can be equilibrium. And so we're going to draw it in compression. Remember, if there are external forces compressing the beam, the internal forces are going to be pushing out. And so, in other words, these forces of compression are going to be pushing towards the end of the beam, and so both of these beams are going to be in compression. And so we could set up our equilibrium equations, but we can also notice how we did with this one is that there's only two forces acting in the x direction and only two forces acting in the y direction. So we know that they have to be equal in magnitude and opposite direction. And they are in opposite directions, so we can just say that our FDCD is equal to 693 pounds. And again, with FBC, it is going to be 400 pounds. Okay, so we're going to write these off to the side now that we've found out two of them, two of the forces in the two different members. So FBC is 400 pounds, and we found that it was in compression, so we'll write a C next to it, and FCD is 693 pounds, which is also in compression. Okay, so now we're going to move on to point or joint A and draw a free body diagram of what's going on here. We'll have our member and our force, and that will be 1,133 pounds from the reaction force at A. And then we will have our member. It is also going to be in compression because it has to counteract the force here, And so it is going to be in compression, and we will call it FAB because it is going from point A to point B. There's no forces in the X direction, as we found earlier with the reaction force here. And if we sum forces in the Y direction, we will find that these two forces are equal in magnitude for there to be equilibrium. So FAB equals 1,133 pounds. And how we've got it written is in compression. And so, kind of just taking a look at what's going on here is we got these three members in compression, and so this force is pushing this way, and it's kind of trying to make the truss push in like this, and so we know that this member BD is going to be pulling it back in, so it is going to be in tension. And so we can pick either of these joints to solve for that and find out what the force is in this beam. And it doesn't really matter which. I'm going to choose point B here. So we'll remember that by saying it's at point B. The free body diagram is going to look something like this, where this is our member FBC, and its force is 400 pounds. It is in compression, so it is pushing towards the end of the beam. So 400 pounds. This one is also in compression, member AB, and it is 1,133 pounds. This member BD is going to have an X and Y component. So we'll draw that like this. We'll call it FBDX and FBDY. And we don't want to forget our external force here acting on this joint, which is 600 pounds. Okay, so once again, we can look at this and notice that there's only two forces in the X direction. So our force FBD sub X is going to also equal 400 pounds. And now we've got an equilibrium equation with our Y direction forces that is going to have more than just two forces. So the sum of the forces in the Y direction equals 0 because it's in equilibrium. And so we have this force, it's positive, Y direction, so it'll be positive, minus this one, which is negative, and then minus this one, our Y component of that beam force, BD sub Y. And so 1,133 minus 600 is 533. Add this over to the other side, and we'll end up getting the F BD sub Y is equal to 533 pounds. And we're going to write that over here, 533 pounds. And so remember that our forces can be represented as vectors, and so using basic vector addition, we can add up these forces, which would be 400 and 533, and the resultant force, which is the force in that beam, FBD, is going to be the hypotenuse of this right triangle. And so what we're going to use is the Pythagorean theorem. The square root of 400 squared plus 533 squared is going to equal 666 pounds. And that is going to be our force in the beam BD. Alright guys, I hope you found this helpful, and I hope you better understand the joint method and how to analyze structures such as trusses. If you did, hit that like button. If you're new to this channel, my name is Preston Palmer with Student Engineering, and my goal is to help other engineering students like me better understand engineering. So if you found this helpful and want more videos like this, please subscribe.